Okay, so as I mentioned, hardness and tensile strength and yield strength under tension are again related to this hardness value. So we can estimate the modulus or the tensile strength or even yield strength based on a hardness test. Why is this important? Well, making a whole new test specimen for a stress strain by tension may not be appropriate. You might have a skateboard and you're interested in its tensile properties or yield strength. And so simply doing a hardness test on that complex surface can often be easier to do. And often it's non-destructive or leads to very minimal damage, just putting a little tiny dent in the material, and this can be acceptable under some circumstances. Okay, so these hardness values by the Brunel hardness value, or as your textbook calls it, the Brunel hardness number. You'll see them with units that are kilograms per millimeter squared, which should make sense to you given the denominator information. That's all in millimeters. And so we're going to end up with millimeters squared as the outcome for the denominator, and our numerator is in load units, which is a mass information there. Okay, so that would be the newtons divided through by the gravitational constant to get the mass equivalence of force. Okay, so with those BHN values or HB values, you can see here that they're related to the tensile strength of the material by taking that value and multiplying by 500. Okay, so that would be for units in PSI. If you want to go to the megapascals, that tensional value is now multiplied by 3.5. Okay, so you can clearly see that these values acquired by a simple dent type test are related to a property from the stress strain curve for a tension test. Kind of interesting. Okay, so what do we got here? We've got some strength values, tensile strength value information here in megapascals that we're used to. Other units are also an option depending on the literature you're reading or the age of your test frame, load frame. And then the hardness values, BHN, are reflected here along the x-axis. So what we're looking at here in the graph are some properties for ductile iron, and the naming scheme is pointing. So we see these two little black lines are pointing to white graphs, white data, that is the tensile strength property, and blue data, that is the yield strength. And here you see that this ductile iron with this complex name, 60-40-18 annealed, is iron that's been characterized to have a tensile property in PSI units of 60,000, a yield point of 40,000 PSI units, and an elongation of 18% for the break point of elongation. So that's where the name comes, 60-40-18. Okay, and you can see there's lots of different types of ductile iron reflected on this graph. Okay, so regardless, the BHN values, here you see your equation from your textbook, is the left-hand side of our equation, and the exact right-hand side of the equation is listed here. And we know that load is, of course, using kilograms of force pushing on our 10 millimeter diameter indenting sphere, and we're going to try to measure that indent and the diameter in millimeters as well, lowercase d. Okay, so as an example, here's a question from your textbook. Brunel hardness measurement has been made on ductile iron. It is the 170.03. So that is this set of data. And it was done using a 10 millimeter diameter sphere of tungsten carbide, so clearly a very hard sphere to indent the iron. A load of 3,000 kilograms of force produced a dent that had a 3.91 millimeter diameter on the surface. Calculate the BHN value for the alloy. Okay, And then the sort of second part is to predict the tensile strength of the ductile iron. Okay, so we'll come back to this graph in a moment, but it looks like we have a little bit of work to do. So we're going to use this equation first and simply plug and chug on the right-hand side to get the BHN value. Okay, so the BHN value is twice the load force divided through by pi d all times capital D minus the square root of d squared minus lowercase d. And we can simply apply values now. So 2 times the load, provided we're in kilograms, so that was 3,000 kilograms, divided through by pi, unitless, times the 10 millimeters, times 10 millimeters, minus the square root of 10 millimeters squared minus the indent, which here was 3.91 millimeters squared. Okay, so hopefully you're seeing here that the square root is going to take this portion to millimeters. We'll take we do a subtraction on millimeters, so we're still in millimeters, and then the product here is going to give the millimeters squared, and that's providing the correct denominator units for the BHN value, which are millimeters squared. Our numerator is pounds of equivalent force, so that's the kilograms. Okay, so after doing this, you should get about 240 kilograms per millimeter squared is your BHN value for this alloy. Okay. Part B asked us to predict the tensile strength of this material. Okay, so we would go to our graph now. We just solved the BHN value is 240, so we're kind of working our way up the graph here, looking for an intercept, and we were asked about the tensile strength. So that is the Y bar information. We got to climb up until we intercept the 170.03 air-quenched ductile iron, and so we're going to intercept that right about here. And so it looks like, without even doing a tensile test, just simply doing a quick little indent test, that we would expect a tensile strength value of 800 megapascals. So hopefully you can appreciate through this example the power of doing a little hardness test for predicting values in a tensile test. Okay, we'll leave it there and we'll see you next time. Thanks.